So, we continue with a discussion on hardware based attacks. In this lecture, we shall be starting our discussion on side channel attacks, which I told you is a new kind of an attack, which is very interesting in some respect, okay? And it is quite informative to go into a little detail about how this actually works. So, in this lecture, which is titled Side Channel Attacks Part 1, here we shall be talking about firstly the general idea what is side channel attack, and then we shall be looking into a little bit detail about one kind of side channel attack, that is called timing analysis attack. Okay. So, let us see what is a side channel attack. You see, in conventional cryptography, we talk about something called cryptanalysis as the art of trying to break a code. Someone has encrypted something, you are trying to break it, you are trying to decode it, but these are done entirely using software mechanism. See, over the communication channel, some communication is going on, someone has captured it and you are trying to decode it. But side channel attack is different. Here what I am saying that, well, let us say I have a device like this. I know that something is going on inside this device, there is some encryption or decryption that is going on inside this device, and somehow I have captured this device. Now, I take my device to my lab, this device to my lab, and in the lab I carry out some kind of experimentation on this device, so that I am trying to find out what is going on inside. So, this is also a kind of cryptanalysis, but the difference is that the device where encryption decryption is going on, that is in my hand, I have access to that device. Okay? This is the main difference. So, this is a relatively new area of research, because traditional cryptanalysis is here for many decades, and in fact, this was proposed in the mid 90s. Since then the importance was appreciated by researchers and this has gained momentum. The basic idea is like this, that you see this picture in this diagram. Here we show some kind of a circuit board. Okay. Some kind of a circuit board is here which is doing something, and you see here we are showing some kind of an oscilloscope, some kind of an instrument which using a probe is connected to this board. So, while this board is carrying out some operation, I am observing what is going on. I am observing some kind of waveforms in the axis of time. So, the basic idea is something like this. We are trying to capture unintended leakage of information. This is the key word, unintended leakage of information during operation. Okay? And this information that you are capturing can be used to extract even the secret key that you are using for encryption decryption with relatively very less effort. Okay? And understanding side channel attacks is therefore very important, because unless you are aware of this, you may be building a piece of hardware which can be very easily attacked in this way, and the secret key can be retrieved relatively easily. Therefore, in future generation devices, this kind of consideration has to be incorporated in a very big way, and all security devices and systems must have this kind of consideration in place. Okay? Fine. So, side channel attack is important because the main point is the developer of a secure product. Suppose I am developing some product related to security. Okay. So, means if I say that, well, my work is only to look at the software, I have to ensure that the software is secure, I do not care about the hardware. That is not the right attitude. I have to ensure the security of my whole device. It includes both software as well as hardware. So, the developer of the product has to defend the product against all possible attack paths, It can be software based, it can also be hardware based. Now, in side channel attack, the point to note is that we are not saying that the cryptographic algorithms that are running inside the devices are bad, are weak. We are not saying that. We are saying that they are mathematically very sound, very stable, we all know that. But when you are doing a hardware implementation of this algorithm, somewhere you have become a little careless, and because of that carelessness, some information is getting leaked out while the algorithm is getting executed in hardware. That is the main idea. So, it is the implementation of the algorithms that is not proper, and some information is getting leaked out during the execution of the algorithm in hardware. This is the basic concept. Okay. So, the typical side channels people talk about, see, side channel, as I said, is nothing but some unintended leakage of information. But what do we mean by information? In this picture, we have showed some of the most common side channels or information that have been exploited by researchers. Like you see, timing, how much time it is required to execute an algorithm, this can be one information. How much power is being consumed during computation of something, you observe the variation of power with time, that can give you some information. Electromagnetic emissions, if you have an electromagnetic sensor sitting on top of a device, so when something is going on inside, you can directly sense the electromagnetic radiations and observe the variations that are taking place. Okay. So, this power consumption and electromagnetic emission variations will be very similar in nature. Heat, if you have some kind of a heat sensor, you can see how the variation of heat is taking place with time, when the chip is becoming hotter, when it is becoming cooler. Similarly, faulty outputs, some of the outputs you can inject some fault, these are called fault analysis attacks. You can inject some faults deliberately by changing supply voltages, making some disturbance in some of the channels. That way you can inject some errors, and because of that some important information might come out, which may be helpful for you in breaking the system. Data coupling, well, if there are some coupled data that are going, you see some, I am just giving a simple example. Suppose you are watching your TV in one of the rooms, okay, and your door and windows are everything closed. So, you are you are assuming that no one is knowing what you are watching, but the video cable that is connected to a TV, let us say that is going and is getting connected to an antenna which is on your roof. Someone outside your house can connect some kind of a probe on that cable and can capture that data that is flowing through that cable. That is what I mean by data coupling, that you can see, that is data coupling. And that data, if I connect to another TV, I can see exactly what you are watching, I can replicate that. If I amplify it suitably and I plug into another TV, I can see what you have been watching inside. Okay. And scan data during test, this is another thing. There are some additional signal pins that are kept in an IC chip that are helpful for testing the chip. During testing, those are required, but when you are not testing, even during that time some data are being coming out of those pins. So, if you measure those signals, actually you are getting some information what is there. Okay. So, all these are typical side channels which people have explored, and there are a lot of research papers on these topics. So, specifically we talk about timing analysis attack because it is easier to understand and appreciate. Now, this kind of an attack was first proposed by Paul Kocher in the year 1995, in the mid 90s. So, the idea is very simple, you are trying to measure the time that is taken for some particular operation to complete. Attacker tries to break a crypto system by analyzing the execution time. Suppose I somehow can tell that, well, it is now an encryption process is starting and here it is ending. So, how much time it is taking? If I can find that out and if I can measure it, that time can give you some very important information. Well, here I shall give an example. And in this process, what does it try to exploit? What are you trying to exploit? You see, if you look at asymmetric key algorithm, you have already briefly seen how public key cryptographic algorithm works. We have seen that RSA, we have mentioned RSA is the most widely used public key algorithm that is being used today. Okay. In RSA, how you do encryption decryption? Basically, we are raising a number to the power of another number modulo some other number. These a, b, n are very large numbers. This is basically how this encryption and decryption both take place. Now, if I can measure the time, we will see that we can get lot of more information about this number b. This b is actually the key, the power, either the public key or private key, whatever, b is the key. So, if I can measure the time, I can get lot of information about this b, and let us see how. The basic way we compute this kind of modular exponentiation a to the power b mod n, this is called modular exponentiation algorithm. And for modular exponentiation, one of the most commonly used algorithm is square and multiply. This I will explain very briefly. Square and multiply is one of the most efficient. You see, when you compute a to the power b, you do not multiply a to itself b minus 1 times, that is very inefficient. If b is a very large number, you need very large number of multiplications to compute a to the power b. So, this square and multiply algorithm, as we shall see, that the execution time will depend when we do a to the power b. If you treat this b as a binary number, it will consist of a string of zeros and ones. Execution time will directly depend on number of ones in this b. It will be proportional to this number of ones actually, in fact. So, here you can use repeated execution with the same key, different inputs. You can try out various ways, you can do various statistical correlation analysis, and with multiple experimentation you can try to recover the key in a complete way. This is the basic idea. Okay. Let us try to understand how it works without going into too much mathematical detail. The square and multiply algorithm works like this. So, I am stating the algorithm here, and I shall be explaining with the help of an example in the next slide. Just remember this slide here. Power x n means I am trying to compute x to the power n. So, I am writing it like this, power as a function of x and n. If n equal to 1, the result is x, obviously. If n is even, suppose if n is, let us say 10, if n is 10, then I say that x to the power 10 is the same as x squared to the power 5, right. So, x squared to the power n by 2, right. Similarly, if I have x to the power 9, I am saying it is same as x multiplied by x squared to the power 4. So, if x is odd, if not x, if n is odd, then it will be x multiplied by x squared to the power n minus 1 by 2, which is 4, 9 minus 1 by 2. So, if we repeatedly apply this formula, then the number of operations can be drastically reduced. You see, here we are carrying out only two kinds of operation, one is squaring, other is multiplication. We are doing squaring here or here, and multiplication we are doing here. Okay. So, if you are not using this efficient method and if you are calculating x to the power n, then you need n minus 1 multiplications. But if you use this technique, then the number gets drastically reduced to approximately of the order of log n multiplication, log n to the base 2. So, it becomes much faster. Okay. Let us work out a simple example. X to the power 13, 13 in binary is 1101. Okay. You see, these each of these will indicate the different powers of x. This least significant bit means x to the power 1, this 0 will be x to the power 2, this 1 is x to the power 4, this 1 is x to the power 8. Now, because there is a 0 here, there is a 0 out here, that is why this x to the power 2 x square is missing, is not there. So, depending on how many ones are there, that many terms will be there in the final product, so many multiplication operations will be carried out. So, for 13, if you just work out that previous algorithm, that previous steps, step by step, powered x 13, x to the power 13 is nothing but x multiplied by x square to the power n minus 1 by 2, 13 minus 1 by 2 is 6. So, in the first step we write it is x multiplied by x square to the power 6. This x square to the power 6 we write again as, since now this 6 is even, x square whole square. So, this we write as x into x square whole square to the power 3, which means x to the power 4 to the power 3. Like this you proceed. This 3 is now again odd. So, this will be x to the power 4, whatever is this first one, multiplied by 1, 3 minus 1 by 2, this square 1, and finally this is 1. So, this will be only x to the power 8. So, whatever we have got here, we have obtained the same result here. So, we need 3 squarings. From x we need to compute x square, then x 4, then x 8, and we need 2 multiplications, because there are 3 terms to be multiplied, 2 multiplications. So, 3 squarings and 2 multiplications. So, the point is, the number of squarings will always be the same. If this x to the power n, let us say if I write x to the power n, if n is a k bit number, then I will always require k minus 1 squarings, that is fixed. But number of multiplication will be equal to how many ones are there in these k bits. So, the total time will depend on the how many multiplications are there. You see, the number of squaring is fixed, number of multiplication is variable. So, if I measure the time, I can get a very fair idea about how many multiplications are carried out. So, I can know how many ones are there in this power n. So, I can get lot of information about the key. Now, this is a pseudo code in C like language that implements that same algorithm. Because the numbers are very large number, these are not integers, I am using a special data type called big number, called big num. If you look at this algorithm, this is a C program, it exactly computes whatever was mentioned here. Now, the point is that suppose I am computing this kind of x to the power n, okay, for some value of n, and during this calculation, well, here I am, the time is all right, but if I look at the total time, you see this pictorially I am showing something. So, whenever there is a 1 in the bit, you need a squaring, also a multiplication. So, you need more time. There is another one, you need more time, another one, you need more time. But when there is a 0, then you need only a squaring, no multiplication. So, your time is less. So, you can say if there are k number of bits, so there will be k number of ones squarings t square plus how many ones are there, I do not know. If m number of ones are there in this n, then m into t multiplication. So, if I measure this time, the first part is constant, second part I can directly get the value of m. I can know how many m are, and if I observe some kind of current waveform on the oscilloscope, I can see a waveform like this. I shall again come back to it later. You can directly see that which are zeros and which are ones if you observe the waveform visually on the oscilloscope. Directly also you can see, and by measuring time also you can directly get how many ones are there in the power. Okay. So, the algorithm basically works like this. You are checking the bits one by one. If the bit is 1, you do both multiply and squaring. If the next bit is 0, you do only squaring, no multiplication. That is how the difference in the time is coming. So, naturally the question arises, if I want to stop anyone from doing this kind of an attack, if I can make these two symmetrical, like if I also add a dummy multiplication here, so that both the branches of this if statement take same time, multiply squaring, here also multiply squaring, then the times will become same and this timing analysis cannot be mounted. So, what I mean is to say is that if I modify this algorithm, that same one, and add a dummy multiplication here, this does not do anything, just a dummy multiplication I am just adding in between here. But what it results in is that all the times now become same. So, you cannot distinguish anything just by measuring the time. So, your design will become resistant to timing analysis attack. This is why we are saying that this kind of an attack relies on carelessness in the implementation, not the strength of the algorithm. Algorithm is good, but because of this feature, this kind of difference was coming. So, if I insert a dummy statement in one of the branch conditions, both becomes symmetrical, they will take same time. So, overall I cannot say how many ones were there in the power x to the power n. Okay. This is how it basically works. So, here is a little bit of math, exactly what I was trying to say. If n is the total number of bits in the key, let us say n denotes the number of bits. So, initially I was saying how many x to the power n, let us say x to the power, let us say a, n is the number of bits, and k denotes that how many ones are there in the key. Then in the normal case, in the previous case, the total time was square, well actually this will be n minus 1, not n, this will be n minus 1, 1 less, and k multiplied by number of so many multiplication operations. Similarly, this will actually 1 less, actually this I am just showed here for just less, this will also be k minus 1, because if there are 3 ones, you are multiplying 3 things, so you will be needing 2 multiplications, right. And t square is the time to compute a square, t mul is time to compute multiplication. But if we include the dummy multiplication step, your time will become something like this. This will be independent of k. This is what we want. We want that the time should not depend on k. This is what we have achieved by introducing that countermeasure. Okay. So, what it actually means is that if the device, as I said, that is carrying out the operation is available with me, it is in my hand, it is available for analysis, then I can take it in the lab, we can gain valuable insight during execution process. And for example, for algorithms like RSA which relies on modular exponentiation, the complexity of brute force attack can be drastically reduced. From order of n, I bring it down to order of log n. It is a drastic reduction, not even log n, much less than that. I can directly tell you how many ones are there in the key. Okay. That is a great saving. And security implications is that, as I have already said, we use this kind of device every day. ATM, that is a device we use, we have so much secret information. If someone mounts a side channel attack setup on the ATM machine, then whenever you swipe a card, your information will be stolen. So, these are all implications of side channel attack or side channel analysis. If someone has the device at his or her disposal, then this kind of an attack can be mounted. And as I said, secure side channel attack resistant implementations become the order of the day, becomes very important. Okay. So, I am repeating, the algorithm that is being implemented may be mathematically very secure, no one is doubting that, but in terms of hardware or software implementation, there has been some weakness. That is why the implementation is becoming vulnerable to side channel attacks. Therefore, secure implementation becomes that much more important, right. So, with this we come to the end of this lecture, where we have tried to give you a brief idea about what is side channel attacks, side channel analysis, and we talked about one kind of attack, timing analysis attack. In the next lecture, we shall be also talking about another kind of an attack, that is called power analysis attack. This we shall be discussing in the next lecture. Thank you.